I'm just going to go ahead and drag all of my header files over. Call it example 2, polynomial. Okay, so we're not going to import a data set this time. We're going to build a data set. So first, let's all build the same data set. So I'm going to go, instead of load data, I'm going to say build data. I'm going to go np.random.seed. I'm going to seed it 2. And if you seed your random number generator the same as mine, then our data will come out the same, and it won't really be a random number. M is equal to 100, which is kind of the number of data points I'm going to have. Now I need to define my x. Capital X is equal to 6 times np.random.rand m comma 1. And I'm going to subtract 3, and that just moves my x data a little bit to the right. And then y is equal to 0.5 times capital X raised to the second x squared plus x plus 2, which is a little bit of an offset, plus np dot random dot rand n this time. The rand n means it's natural random, not uniform random numbers of m. And that's just going to add some naturally distributed Gaussian noise to that data. And now I have x and y data, so I can go plot the data. plt.figure, plt.grid true, plt.scatter, capital X comma y, plt.x label, my favorite x label of all time, quotation x, plt.y label, quote y. Those are great x and y. Okay. X and y must be the same size. What did I do wrong? Oh, yeah. So comma m, comma 1. Yep, that's definitely needed. Okay. And then that's kind of our data set. Hopefully you have something that looks like that. I mean, it's a little cheating to use a polynomial to build the data and then use a polynomial to model the data, but let's go ahead and hope it works.
Line 34. Yeah, it's got a white label.
My incompetence is showing. Just kidding. Or not. So, okay. Now let's go ahead and perform polynomial regression. So generate x squared that we use in the model. So let's first generate x squared values. So that's going to be capital X poly underscore manual is equal to np.h stack. I need a tuple for this, so it's x comma x squared. And that should give me the x and x squared data that I'm looking for. So x poly is going to give me all of my x values and then their associated x squared values, right? So if I look at this on what we drew out earlier, I get my x value here on the y-axis, and then I get my x squared value, sorry, my x value on the x-axis, and my x squared value on the y-axis. So that works out well. We can go ahead and build that manually. But maybe instead of building it out manually, we just want to use sklearn pre-processing to help split this out. So I can go poly features equals sk.preprocessing dot capital P polynomial capital F features. And that's going to build my polynomial features for degree 2, include bias, which is my offset. We're going to set that to false. And hit F5. And now what I've created is a SK feature-based polynomial that will do all of this kind of pre-processing for me, so I don't have to do it by hand. However, we haven't trained this yet, or we haven't given this any data, right? All we've done is set up a structure for it. So now let's go ahead and feed it some data. And that's going to be capital X underscore poly underscore SK is equal to poly underscore features dot fit underscore transform transform X, which is our data set. And now if we look at this, we have this XPoly manual that we formulated on our own. And then we have the one that was formulated for us by sklearn. And they should hopefully be pretty close. They don't have to be exactly the same because of ordering, but it looks like they are ordered exactly the same. And so this is our x and our x term, our x squared terms. Why might you want to use sklearn instead of doing it by hand? Is because we're only doing an x squared polynomial. But if you have an x cubed, then you have x, x squared, x cubed, and then all of the ways that you can combine those two. And so it gets quite big quite fast. So I know that kind of came out of nowhere. We either have to start with math first or coding first, and we'll try coding. I think it's helpful to actually physically do it and then maybe look at what we're doing sometimes. But okay, so they do the same thing, which we just showed. And now we can go ahead and plot them together. So plot the features here I'm just going to go ahead and copy this plot down. And what I'm going to do is I'm going to plot this twice. And this is going to be plot x underscore poly, open close square brackets, all of my columns for row 0, x underscore poly, open close brackets, all of my columns for row 1. X poly is not defined. Oh, X poly, well, they're exactly the same, right? So let's just do, since they are the same, let's rename them. And the goal here is not actually to write the world's cleanest code. It's to kind of keep it simple as we follow through. And so this is what my data starts to look like. Maybe we should put some legends on this. So let's do label is equal to data for x. Label is equal to data for x squared. plt.legend. Right. And so obviously we don't have any negative values for x squared, but we do for x. We don't get any negative values for x squared because the aspect of squaring it takes away all of the negative values. All right, let's go ahead and train some linear regressors to cut through this line. So we're going to say model is equal to sk.linear regression. We'll use a closed form. And then model.fit x poly comma y. We're going to fit that model. And now I need to do my x model. But for one of them, let's go for underscore 1, I have np.lin space from -3 to 3. That's because my x model has positive and negative. But my other one, we're going to call x model 2, just goes from 0, it goes out farther. So let's just say 0 to 9. And so I can go ahead and run that to make sure my model sklearn has no attribute linear. Do I need a capital L?
I think it's linear underscore model.
Underscore models. sklearn linear underscore model singular. There we go. Model coefficients. All right, so now I just want to get my model coefficients out of this. So I'm going to extract those as model. Let's put a label on it. The model parameters are model coefficients are equal to model.coef underscore. And then model underscore intercept is equal to model.intercept underscore. And then we can just go ahead. I actually kind of want to know what they are. So I'm just going to say print model coefficients and print model intercept. And we'll see if that shows up. Okay, I got model coefficients. I have a parameter for my x and a parameter for my x squared. And then I have my intercept. So those are my 3 parameters now. And I can go ahead and draw those out. So we're going to go capital Y underscore capital X1 is equal to model coefficient. So 0 should give me an ordered pair. If I can get it to run. Yeah, so it gives me an ordered pair. And right now, I just want the first one, 0, times x underscore model underscore 1 plus model underscore intercept. And do the exact same thing for the second one, but take the second coefficient, because one coefficient is for the x and one coefficient is for the x squared. And now I should be able to run that and I get data for those 2. Oh, that's got to be x2. I get data for these, so I can go ahead and plot. All right, I have a nice linear line. So that's fitting through, I don't remember which one I clicked on, but it's fitting through either my x data points or my x squared data point. So let's plot all of these together to see which one it fits through. Now plot the linear models. plt.figure, plt.grid true, plt.scatter. So we want to go capital X underscore poly, and we want all of our features for row 0. Sorry, for column 0. And then we want Y. Why am I retyping this? This is the same plot as up here. Let's do that. All right, so this gets us to the plot we had before, which is our data. And now what we want to do is we want to add our linear fit lines, right? So we're going to go plt.plot x underscore model underscore 1 comma capital Y underscore x1 comma, going to make it a dash dash line, label equal to linear fit of x, capital X. Put that one in math mode too. And now I can just copy that whole thing and extend that out like that. Okay, so I have acquired a linear fit on my model that doesn't look correct, does it? That bottom one shouldn't probably be cutting through the middle. Did I feed it the wrong data? Do I need to refeed it something else? Okay, here we go. Model 2. How about that? Aha, there we go. That orange line wasn't cutting through the middle, right? So I've made a regression model for one set of features, that's x. I've made a linear regression model for another set of features, that's x squared, right? And now together, these two models can build what I need. So again, let's say build out the full model. Remember that we had assumed y or y hat is equal to x squared times a plus x times b plus c, right? Is that what we had assumed? Okay. And so that becomes y underscore polynomial equal to model underscore coefficient 0, 1 times, let's use x underscore model underscore 1 squared plus model plus model, sorry, plus, yeah, model underscore coefficient 0, 0 times x underscore model, it's going to be model 1 again, plus model intercept. And then we can go ahead and plot all of that. So let's make sure that runs real quick. So plt.figure. This is the same as my initial plot. So I'm going to go ahead and copy that down. That is not my initial plot. I'm going to go ahead and copy this one down. And then after my scatter plot, I am going to go plt.plot x underscore model underscore 1 comma y underscore polynomial. Let's give it a cool color, maybe red and dashed. I think that'll work. That does not look right. Okay.
I think in your x squared term, you multiplied it by 22 instead of,
Could be an issue.
well, it's now just multiplied by 2.
It needs to be squared. I was like, man, that's an awfully linear model we got there. Okay. And that is kind of mathematically or code-wise how we build a nonlinear polynomial regression.